is part of biologically motivated machine learning. There are other areas like that, including neural networks, which is what generative models are based on, as well as swarm optimization and colony optimization, other methods like that. So you look at biology and you notice that it's doing pretty well in certain problems. And then you try to abstract that and build computational model to emulate that. That's the motivation for it. But in a big scheme of machine learning, most of machine learning is about supervised learning. So you collect big data sets where there are examples and then there are targets. What do you want to do with that example? For instance, a picture of a dog and then a labeled dog, or text that's categorized somehow, or even the generative AI models are trained by just predicting the next word. The next word is always there. You are backpropagating your gradient using gradient descent from the next word. So you have supervised learning techniques. That's one big category and very successful category. But then there's a category where you get very weak feedback. You only know how good your solution is, not what it should be.
We want our AI to be aligned with the way we value decision making, basically. So if we have some KPI, we have some outcomes that we care about, we want the AI to actually be solving for those outcomes. And so those outcomes, and it's always plural, it's always more than one. If you're going for more sales, you also want to control your costs and improve your revenue. And these outcomes are often not aligned. You look at the pandemic, you want to reduce the number of cases, but at the same time, you don't want to have a major economic impact on people's livelihoods. And these kind of are not always aligned with each other. And evolutionary computation, evolutionary AI is very good at coming up with strategies that are balancing, give us a balance of multiple outcomes, and let us then choose which balance of the outcome is more interesting to us.
The difference is that most machine learning, including the generative AI models, they are based on interpolation between things that you already seen and predicting decisions that you already seen before. Like, here's a picture, what's in it? Well, you've been told that there's a dog, and you now can recognize many different kinds of dogs. But that's really leaving money on the table if you leave it at that, because you can also use AI to come up with solutions, not just to predict what will happen, but actually give you a suggestion what you should do about it. And that's what evolutionary AI in particular is really good at. We have a population, like in biology, a population, and it's evolving towards better behavior. We reward the population if it comes up with decisions that lead to better outcomes. And then we use mechanisms adapted from biology, like crossover and mutation, to come up with new solutions. And this way, over time, we can discover solutions that are actually pretty hard to discover, even those that human designers would have a hard time coming up with.
The way we set these systems up is by first identifying those outcomes, then coming up by using AI and generative AI and so forth, coming up with what we call predictors. So in the presence of some decision, what would the outcome be? So for example, if we shut down schools, how is that going to affect the economy? How is that going to affect the number of cases? If we shut down work, if we vaccinate, and so forth, right? So for different strategies that we take, what is the outcome going to be? Those are the predictors. But predictors alone are not enough. If you know what's going to happen in the future, you still don't know what to do and in what order and how much of which in order to find that balance of outcomes. And that's where evolution comes in. So evolution basically searches the space of all possible decision strategies. And that's a very, very large space usually. And it searches it very efficiently. So we can quickly come up with those strategies based on what the predictors are predicting for us. And how do we put this to work? Well, at the point where a decision maker wants to make a decision, it can say, here's the state of the world right now. For example, here's the state of the pandemic, or here's the state of my business. And the prescriptor, quote unquote, which was what we just evolved using evolutionary computation, is going to tell us, here's what you need to do in this state, and here's what's going to happen if you do it. So it gives that sense of collaboration as well. Not only am I telling you what I think you should do in order to hit the balance of outcomes that you care about, but I'm also predicting what's going to happen if you do so. So therefore, you can come in and modify it and say, well, closing schools right now is an option because it's summertime and schools are off anyway. So let me actually do that and see what happens. So you can actually pull the various different levers, make some changes, send that to the predictor, and the predictor will then say, well, here's what the outcome is going to be if you do that. It's kind of conducive to the way we make decisions. We kind of run various different scenarios hypothetically, and we come up with the best way to make a choice. So evolutionary AI, the way Risto and I just described, really works well in an environment where you can identify the outcomes and collect the data on an ongoing basis and make these optimizations.
Evolutionary AI have some advantage over traditional decision-making technologies. They can, because those algorithms can create entirely new solutions and not derive from existing knowledge. So if you don't borrow from existing knowledge, you're allowing to discover strategies that human may not have thought about. So that's the creative process and this opportunity. At the same time, they can optimize multiple objectives, right? Because if you have a goal and a solution space and you want to look at multiple objectives, you can actually optimize for that on multiple objectives. The fact that there is creative process and intuitive, the models that are coming out of that are probably more transparent and more explainable in general because of that reason. So basically, it's a complementary approach to traditional black box deep learning models that are using only data to behave, but you don't have any explanation. So there's this attribute of evolutionary AI to me. It's somewhere between deterministic Bayesian models and quantum mechanics models, right? We can actually go and find multiple objectives and multiple space. You can basically discover solution spaces, but at the same time, they can be explainable and transparent. So these are the two attributes that I've observed makes a difference.
So you have to start with something to create the predictive model like Babak suggested. So we planted about 300 recipes, plants according to different ways of controlling the light and water and nutrients and temperature and so on. Those were the ones that the biologists came up with, the usual suspects, as well as some exploratory examples, very different kinds. And we have now 300 points about how the plant grows under different conditions. And then we built the predictive model, trained, I think it was a symbolic regression model at that point. And now when we have a predictive model, we can explore widely. We can come up with crazy recipes and ask the predictive model, well, what would happen in this case? What would happen in that case? And this way, find those solutions that are hard to find. And it happened actually that we had set up a limitation of 6 hours of darkness, and all the solutions that evolution was exploring were right at that boundary. So at that point, we said, well, open it up, try other solutions. And these solutions are nothing but just simple vectors of numbers. How much light, what kind of light wavelength, how much water, and so on. So those are numbers that evolution modifies using these operators of mutation and crossover, taking two solutions, parts of two solutions, putting them together, as in biology, in crossover. And this way you are exploring the space intelligently, taking into account what you've seen already, how well they worked, and trying more solutions like that. And in that sense, then, when we open it up, evolution pushed the solutions all the way to the end, and we had 24 hours of sunlight in these solutions.
So evolutionary AI and traditional machine learning models, there are areas where when we have complex decision making, we have more constraint to deal with. For instance, rare diseases, right, as an example. How can you work on rare diseases from a pharmaceutical perspective? There is a number of drug candidates that need to be identified. The cost of drug research is huge, and the market is not that large. But you have to somehow deal with diseases that are prevalent in the world. And so how you can do that? So traditional models are not adapted, but when you think about if you want to find a cluster of potential molecules, right, for a given drug, and add additional constraints, for instance, for toxicity, for instance, or for including genetic background, evolutionary AI or this its approach will help actually accelerate the drug discovery part and add constraints.
Then, as Cognizant, we can come in and help businesses provision that data. If there's third-party or public data that needs to be coming in, we can bring that in, clean the data up. Much of that could also happen using generative AI. And so there's a process to actually make that end-to-end prototype, if you like, make it real. Cognizant has a very, very strong presence, as you know, in India. We have colleagues in India that are well-versed in using evolutionary AI and neuro AI.